Started then. All right, welcome everyone to this week's IQS seminar. We are happy to have Sacha Greenfield here to talk about the Zeno effect. I've known Sacha for many years. Sacha started their career as an undergraduate at Carleton College and ended up as a summer research intern here at Chapman. We're moving on to a graduate career at USC under the advisement of Eli Levinson Falk. Sacha is graduating relatively soon, so if anyone is looking for a very talented up-and-coming researcher, be in contact. So, Sacha, without further ado, tell us all about the Zeno effect.
And the anti-Zeno effect. So, it's Justin. So I will be discussing today our recent work on unifying Zeno and anti-Zeno effects. And this was done in collaboration with Archana Kamal at Northwestern University. So if you're familiar with the history of the quantum Zeno effect, its namesake is the Greek Zeno's paradox. So in this paradox, it's a paradox of motion, where you imagine if an arrow needs to hit its target, first it must move halfway to the target. Before it moves halfway, it must move halfway to halfway, and so on. And so the paradox of motion that the Greek philosopher Zeno put forth is that if it takes a finite time to traverse any finite distance and you can continue dividing the distance in this way, how does the arrow ever move from its initial location? So the quantum Zeno paradox is kind of a modern rendition of this paradox of motion, where if you actually take rapid projective measurements of a quantum system, as you take the spacing between those measurements to zero, you'll end up preventing evolution from the starting point. Of course, Greek Zeno's paradox is empirically disproven because we know the arrows actually do hit their targets. And we can just conclude that Zeno didn't know calculus and series and all the other fun techniques that we have today. But by contrast, the quantum Zeno paradox is actually experimentally observable with the caveat that all measurements take a finite amount of time. And because when we consider it for finite time, we instead call it the quantum Zeno effect. And instead of fully preventing evolution, it will simply suppress the evolution. And we'll get into more what exactly that means. And you can think of this as something which is naturally evolving when measured strongly enough evolves less. But we'll also talk about the quantum anti-Zeno effect, which is for possibly historical reasons or otherwise much less well known, which is that rapid projective measurements can actually enhance the evolution, given that naturally the system is stuck in its initial position. Then if you measure it below a certain strength, you can cause it to get unstuck from that initial position or initial state. So we'll talk more about this. So this is where our survey comes in. So I just want to kind of hear from a few people, what is your understanding of the quantum Zeno effect if you have any past exposure to it? And you can just say a sentence of what it is or where you might see it manifesting. There's also another question, or you can answer your own question.
Well, anti-Zeno effect is much more complicated. Zeno is rather much more easier to understand, at least in my perspective. So when you take a little bit theory, and you can easily show that in any non-decaying probability, how it looks like. So initial stage is slower than exponential. So this is general case due to the, I think, correctly Heisenberg relationship of uncertainties, uncertainty relations, reducing to that. So if you measure it with a small time, you are always experiencing that system initially decays slower than exponential. So in this intermediate range, you see exponential decay, and then if you let system evolve for a long time, then exponential approximation does not apply. So if you measure always in this region where you decay slowly, this is how you actually cannot see. And this is why you always see slower evolution. Otherwise, if it is exponential all the time, then you cannot get anything. At least this is how I explain it to myself.
Yeah, I think that's like a critical point too of like, it really has to do with this evolution in that short time in which you're measuring. And so we'll see like there's actually an intuition we can get around the anti-Zeno effect that comes similarly. Anyone else want to chip in with their understanding or an example of where it arises? We can also move on, but.
Oh, you want me to? I say the quantum Zeno effect is a proof of contextuality. There you go.
Wow,
Get that-
okay, I'm
get
not
that talk
gonna,
a few
I'm
weeks
not
ago.
gonna, maybe we can unpack that afterwards. Okay. So, just to present the traditional formulations, as you said, like it has to do with this initial evolution before you do the measurement. So in the traditional formulation of the quantum Zeno effect, we look at a unitary evolution and what happens if you measure repeatedly, kind of a little bit after that unitary evolution has had time to advance. And this is traditionally a selective approach. And so we look at actual measurement outcomes. So we see that the state is repeatedly projected back to the initial state. And this was how it was originally formulated in the 1977 paper that coined this term Zeno effect. By contrast, the anti-Zeno effect, which arose much later in 2000 and the late 1990s, has to do with repeated measurement enhancing evolution. And this has traditionally been looked at in a non-selective way. So they don't actually look at trajectories or the probability of staying pinned to an initial state. It's more about what does an ensemble or an average behavior do. So the way I'll structure the talk is I'll kind of talk about how these two subfields, you can think of them as Zeno and anti-Zeno, but more broadly, we'll also look at how measurement selectivity plays into this, how these two subfields arose and how we entered into this conversation. I'll talk about a minimal qubit model that we developed where we can see all the various aspects of these effects as they've been examined in various subfields, which allows us to unify various phenomena that we see called the Zeno effect or the anti-Zeno effect, which are actually quite diverse. And then I'll talk about recent experimental developments and applications from this framework. So a tale of two subfields. So this is not always appreciated, but von Neumann actually was the first one to point out the existence of a Zeno effect in his original treatise on quantum measurement in 1932. And he actually pointed out a Zeno dragging phenomenon where he said that if you take a rapid number of measurements where the measurements are slowly changing in their axis, you can drag one state into another with probability that goes to 1 as you make the measurements infinitesimally close. And we now know this as Zeno dragging. That was odd. But this was kind of ignored or not picked up until around 1977. Misra and Sudarshan were examining the same sort of question, not really in conversation with von Neumann's work, but in conversation more with recent work. And they looked at how instantaneous projective measurements could prevent evolution. And in their case, they were interested in preventing decay. And this is when they coined the term the Zeno's paradox, because they felt that it evoked this paradox of denying the possibility of motion. They weren't sure, like, is this a real effect? Or is it something wrong with our assumptions about measurement? But they really emphasized that the meaning of the probabilities that they were examining had to do with the outcomes of this continuously ongoing measurement during the entire interval of time. So they were interested in this kind of selective record. So it was about 23 years later that this was finally experimentally studied by Itano et al. And later there were some other experimental studies, for example, Nagels et al. In 1977. But what was curious about them was they didn't actually utilize the measurement record. They just looked at how, if they were measuring, how that suppressed the evolution on average, if they just measured at the end and saw what the measurements in between had done, but they didn't actually track how the measurements affected things. And this sparked a lot of debate in the 1990s about the role of projection or the measurement collapse hypothesis. So for example, right after their paper, there was a paper by Perez and Rom that pointed out there's nothing actually paradoxical about the quantum Zeno effect. It's just a dynamical interaction between the measuring apparatus and the quantum system, and everything follows from there about the transition rates that are involved. And this debate and discussions continued such that 6 years later, it was said that nowadays most physicists tend to view the quantum Zeno effect as a purely dynamical process. So it actually became relatively well understood in this conversation that you could understand this without measurement collapse. But they pointed out, that's actually not quite what Misra and Sudarshan meant. That's not how they originally formulated this effect. So this hasn't actually gone and been tested yet. And this was the context out of which the anti-Zeno effect arose or was pointed out by Kaufman and Kriski. They noted the existence of this anti-Zeno effect by reasoning about spectral overlap with a detuned bath. And this was a purely ensemble reasoning. And so the reasoning here, if you're kind of familiar with what a spectral, the spectral effects of measurement, the idea is that by measuring a quantum system, you're actually going to effectively broaden the spectral line of that system. And this will change how it interacts with other spectral features in the environment. So their point was that when we think about a Zeno effect, the spectral line of the bath, and these are figures from their original paper, the spectral line of the bath, we're kind of assuming it's on resonance with whatever the system is, so that when we measure the system, we're going to broaden the system spectral line, which will reduce the overlap and thus reduce the interaction. And this will suppress evolution of the system or decay of the system into the bath. Whereas with the anti-Zeno effect, they said, but if you just detune this, this bath spectral density from the system, then when you measure the system, which is originally detuned from the bath and not interacting with it, actually comes into resonance, in a sense, with this detuned bath by virtue of being measured. And so you'll actually see a region where you get enhancement of decay into this bath as it comes into resonance. And then you'll get more of a suppression effect once that increase of overlap has kind of exhausted itself. And this was all, again, from this perspective of measurement as an act of coherence breaking, not necessarily involving wave function collapse. And just thinking of it in terms of a dephasing. So over time, the literature seems to have grown quieter about the importance of this measurement record, but inconsistencies and misunderstandings kind of persist between fields. For example, there was a recent paper that was actually one of the key papers studying the anti-xeno effect experimentally in recent times from Harrington and Murch that basically actually did a whole experiment to check, is projection onto an eigenstate essential, like is extraction of information essential, despite this debate that already had proceeded. And I think this kind of reflects the fact that we really, from a trajectories perspective, tend to think of the Zeno effect as a selective phenomenon, not really thinking about how it manifests in an ensemble. Whereas in other communities like the cat qubit community, this is widely accepted, and just almost what people mean by the Zeno effect is that there are dissipative dynamics that stabilize a certain subspace. They aren't really conditioning on measurement outcomes, because that would just be too much work for something that is fine just being a dissipative process. And I'll talk a bit more about these applications near the end. But this historical development was kind of interestingly mirrored to our own questions as we came into this. Of course, at that time, we hadn't really read the literature and we hadn't gone through this process. And so we kind of stumbled into these questions on our own, realizing that we came in with different assumptions. And so this all started when Archana reached out to Eli and was like, you know, we recently did this experiment where we demonstrated enhancement of evolution using engineered dissipation, which is the anti-Zeno effect. But can we get this from like actual measurements, like with trajectories? And so we were discussing this at the March meeting, and I was like, well, if you mean evolution condition on a measurement record, it's just going to give you the same ensemble. So you're going to see the same result. So like, what's the question exactly? And of course, Justin pointed out, it's trivial. It literally is trivial, like trajectories trivially average to the ensemble. But we also ran into this difference in understanding of like, if anti-Zeno doesn't involve suppression of motion, why are you calling it Zeno? So Zeno is when decay rate decreases with measurement, so anti-Zeno is when it increases. This is the canonical understanding from the subfield that Archana comes from. Whereas in the trajectories community, Zeno is when measurement pins trajectories to an initial state. Decay rate is an ensemble quantity that doesn't apply. Of course, Eli, wanting to just let's get to it, pointed out like, well, if they average to the same thing, it's kind of all the same thing, right? Trivially. But this did raise this really interesting question of what characterizes anti-Zeno in trajectories, which it turns out hasn't really been explored because of this historical kind of coincidence of how the fields arose. So that was kind of the question that we started with, which led us forward. So the conclusion that we came to is that these effects are tightly related, as what has been known historically, but has kind of been forgotten or overlooked. And they're just relevant in these different contexts. And that these anti-Zeno trajectories by historical coincidence have kind of gone unexplored. And so we filled this gap by providing a unified framework of these effects through a minimal qubit model that captures these various perspectives. So that's what I'll talk about now. So it's a very simple system. It's just a damped driven qubit. So you have two states with a Rabi drive and a along sigma x, and a orthogonal evolution along sigma z, which if you're thinking of this, say, as a transbond qubit or other system where you tend to where you're going to try to drive Rabi oscillations resonantly, you can think of the delta as like a drive detuning, basically. And then we have a measurement of sigma z, and we have the option to block or discard the measurement outcomes, which makes it non-selective because we can only really talk about what we know on average. And you can think of these various, you can think of these as kind of axes of what measurement options we have. So we have discrete or continuous measurements, discrete being projective, and we have selective and non-selective measurements. And so in the case of selective and discrete measurements, we're going to get unitary evolution that's interrupted by projective measurements. We'll get a discrete record that is a random bit string, basically. In the selective and continuous case, instead, the evolution is continuously perturbed by the measurement, and so we'll get instead a continuous noisy homodyne trace as the record. In the non-selective discrete case, without the record, our unitary evolution is just interrupted by discrete dephasing events. And in the continuous case, we just get a continuous damped-driven evolution. So I'll kind of walk us through these, and you can just keep in mind that this is kind of the area where trajectory Zeno has tended to look, and Zeno and anti-Zeno has historically looked in this sector. But there's also another dimension that picture doesn't really capture that is really important in our model, which is whether we have standard or stabilized evolution, which has to do with this detuning that's added in here. And it'll become clear as I go on what the role of this detuning is and why we call it standard versus stabilized. So just a bit of formalism for how we're modeling this. If we have a qubit state psi, we'll measure so this is the projective measurement case, right? We measure a bit r just according to this probability, which will just extract essentially the probability of 0 or 1 from the state. We get it from this projector, and it will result in the qubit being projected to 0 or 1 and renormalized by the probability of getting that outcome. And that record will be this random bit string that we'll see is correlated with the qubit evolution. So this is what trajectories in this model look like. And what you're looking at here is the population of the initial state of the qubit as it's evolving under both this unitary Rabi oscillation with a detuning of 0 and these pulse measurements that are happening at this interval delta t. And each of these plots is changing the interval of that measurement. So the measurement is becoming more frequent. And so what you can see is the standard effect you expect for Zeno, which is that as you make the measurements more frequent, eventually you move into a regime where you see pinning and rare jumps. And eventually the state just becomes pinned to the initial state. And this happens past this critical point, before which you aren't quite sure what you're looking at because you just have oscillations that are interrupted now and then with a projection. Now, if we take this same formalism and we average over the possible outcomes R, what we'll see is that we essentially get non-selective projective measurements, which is just a periodic zeroing out of the qubit coherences. And so we're taking the coherent evolution and just turning it into a mixture of those two probabilities. And you get the ensemble average that corresponds to those trajectories. And what's interesting is that once you move into the higher and higher measurement strength regimes, you really see exponential decay with a decay rate that gets suppressed as you increase this measurement rate. And so we say that in the ensemble picture, this Zeno pinning kind of criterion of what is the Zeno effect becomes this suppression of exponential decay. And this is kind of the definition that, for example, Archana was coming in with is how is this exponential decay rate getting suppressed? And I think one thing just to keep in mind is that you can, because this is an exponential decay and these are telegraph processes basically, you can think of this exponential decay rate. It's equivalent to the jump rate of these trajectories up to a factor of 2. So they're tightly related. Now, when we go into the continuous measurement formalism, it's quite similar, but this time we have a probability density for these continuous outcomes. And our POVM is given by this Bayesian measurement update operator, which just tells you how your state gets updated given acquisition of this measurement value, supposing you were in 0 or 1. So it's just updating your state as though it were a prior probability distribution. So this results in qubit back action, just like in the projective case, except that it is weaker. And you get this noisy homodyne trace. And in the limit of a small, of the time step going to an infinitesimal, you get the Ito stochastic master equation. Now, these trajectories look similar, but more continuous, and probably very familiar to people who are used to working with trajectories. You have noisy monitored oscillations, and as you increase the measurement rate, these kind of transition into a region of jumps. And then as you further increase the measurement rate, the jump rate gets suppressed and the pinning becomes more tightly confined to the initial state. Now, when we make this non-selective, this is essentially equivalent in this stochastic master equation to averaging over the noise realizations. And so you just get a Lindblad dephasing. And so you can kind of anticipate what the ensemble average of these trajectories will look like. It's just a damped driven evolution where there's an underdamped evolution when the Rabi drive is strong compared to the measurement rate. There's a critically damped point and then the decay rate again gets suppressed. Yeah.
C and D, if I will consider some intermediates, say gamma is gamma critical and 10 gamma critical, do you have 3 gamma critical plot?
I do, but not in this presentation, but what it will look like.
It's not clear how it is evolving from C to D.
Yeah. So like you can see how this, in this case, it looks kind of telegraphic, but there's a lot of kind of noisy escapes. It'll look quite telegraphic in this transition region. Like basically it will look more and more like an idealized telegraph process with the noise just becoming
It's interesting to
Less.
take it. Okay.
yeah, but I can show you later what such trajectories look like. So I think, again, it's an interesting point in terms of how different communities would look at the Zeno effect, because I think from a trajectories perspective, once you get into this region of there are jumps and pinning, you basically just call that the Zeno effect. Whereas from more of the Zeno anti-Zeno perspective, the Zeno effect is how this plot morphs into this plot. It is how the trajectories become more and more pinned, which is a subtle difference, but it's still a difference. So thus far, we've really seen just these standard formulations of the quantum Zeno effect, so it shouldn't look altogether surprising so far. This is population transfer that is suppressed with measurement. But what about population transfer enhanced with measurement, or the anti-Zeno effect? And so since these effects were originally studied with a detuned bath, like we'll add in a detuned drive, since our drive is basically providing the role of this competing evolution, and we'll be able to see an anti-Zeno effect. And so in this stabilized non-selective evolution, what we see is that, so this, in this plot that you're seeing here now, the measurement rate is increasing kind of counterclockwise. So up here is a very weak measurement. Down here is a very strong measurement. And you may notice like these look very similar, the weak and the strong measurement, but the reason is that they're both very strongly confined to the initial state, but for very different reasons. So in this case, of course, it's a strong measurement. The measurement is confining the state. But in this case, it's the detuning or this Hamiltonian evolution that is confining the state. So the way to think about this is that, you know, you have this strong sigma z evolution, and it commutes with the measurement. So it has the same states that it is stabilizing as the measurement has. So because this is very strong, when the measurement is weak and this delta is much greater than omega r, it's going to stabilize the states near the poles. Your Hamiltonian axis is very close to your measurement axis. But as you increase the measurement rate, the measurement will kind of temporarily destabilize that. It basically kind of grabs onto this Rabi oscillation part that still is oscillating a little bit, which we'll look at in trajectories in the next slide, and allows for this transfer up until this critical point at which there is suppression again. And so you essentially, in this stabilized case, which is what we call when you add this detuning that stabilizes the initial state itself, you get an anti-Zeno regime so long as your measurement strength is weak enough. And then you get a Zeno regime once you move well past the oscillation frequency of your Hamiltonian. So like I said, the stabilization mechanism is different between these two cases, but the kind of overall qualitative effect will be the same.
Any estimate for gamma critical?
It is omega over 2, I believe.
Over 2?
Yeah. I actually, it's not just an estimate. I always forget whether there's a factor of 2 or not.
Omega over E, 2.7, no?
No,
No, 2?
it's exactly proportional,
Okay.
but I can't remember what the factor is. Which is why I was being vague about it. So, yeah, in one case, so in the case where we have where we're in the standard case, there's a different critical point from the stabilized case, and they're different by a factor of 2. The stabilized case, I think, is omega, like the dressed oscillation rate, and the standard case is omega over 2.
Okay.
So if you look at these trajectories for the Zeno, anti-Zeno, what you see if you look on the right time scale is something that's really quite striking, which is essentially that it seems kind of like this evolution that is confined for these weak measurement rates gets unconfined as you increase the measurement rate up to this critical point, and then gets confined again, which is exactly the mechanism that was just described for the ensemble. But it's really striking in the trajectories because it really is a telegraphic process that just has some dressed oscillations on top of it. And so this you can think of as a resonant tunneling effect, which is actually very similar to work out of Andrew Jordan's group, which I'll mention at the end of the talk. But basically that your measurement, in a sense, unpins your state before it pins it again. And to get intuition for this, we can look at these at pulsed trajectories for the anti-Zeno case, which can give, I think, a very clear sense of why this is happening this way. So like I said, in this case, if you look at your block, your measurement axis is along Z, and your Hamiltonian is slightly tilted away from it, and in this stabilized case. And so if you have no measurement, you're confined up near the top of your sphere. That's just where your state is going to evolve. But if you add a measurement in, you now create the possibility for the state to jump to the opposite stable oscillation. And the more frequently you measure, the more possibilities for making that jump to the opposite dynamical state you're giving the system. And so for measurements that are already rare compared to this oscillation frequency, you're actually going to see jumps that increase with the measurement rate. And this is this resonant tunneling effect I mentioned. And you don't really see this in the standard case without a detuning because you're already getting oscillations between your states. There's nothing really preventing population transfer per se. And so you're only going to see a distinct suppression once you pass a certain measurement rate. Whereas in the stabilized case, you get both apparent suppression and enhancement. And just to drive this point home, like in the ensemble, the way you see this is that you have a overall decay envelope that does get enhanced with the measurement, but this doesn't have to do with the population transfer. It's just this envelope. And as you increase the measurement rate, this envelope gets faster and faster decaying, but the population transfer itself is not impacted. Whereas in this stabilized case, the population transfer is enhanced by adding in this measurement. And so the way that we formalize this is by really pointing out this mixing rate, this envelope that is suppressed or enhanced with the measurement. And we define Zeno and anti-Zeno regimes in terms of this rate, which we call the Zeno response. How this rate responds to the measurement. And so in the case where there's this derivative, which has this negative sign, is positive, we get a Zeno regime. In the case where it's negative, we get an anti-Zeno regime, since this tells us how this envelope responds to the measurement rate. In the stabilized case where we were just looking at, this corresponds very intuitively to what we were looking at in terms of enhancement and suppression, which is this curve here. This is the mixing rate and how it's responding to gamma, the measurement rate on this log scale. In the standard case without a detuning, we still get the same kind of structure, but again, it's not going to correspond to this interesting population transfer enhancement. And as Justin pointed out, this is really interesting. The interesting point here from kind of a trajectories perspective is that when you're weakly measuring, you're still actually enhancing this mixing rate before you're suppressing it. You're just looking at it. It doesn't show up quite the same striking way as you're getting in these anti-Zeno, stabilized anti-Zeno effects. So in the last 10 minutes, I'll just talk about how this connects in with some recent experiments and applications. And we'll see that the applications are actually extremely diverse, but you can always kind of put it into this framework of, is the measurement selective or non-selective? And it really doesn't quite matter actually whether it's selective or non-selective or how exactly you're implementing it, apart from the kinds of things you can do with the measurement record. But I think one thing I'll just highlight here is that in our minimal qubit model, we looked at two states where you're suppressing transfer between them. And more generally in these kinds of applications, sometimes it's two states you're interested in, but more often it's actually like two subspaces. So you'll have a measurement that kind of detects whether you're in one subspace or another. You could think of this as a code subspace and an error subspace, or maybe you just want to create a state with a certain number of photons, which we'll see. So I'm going to start with an example that probably will be the most familiar to some people in this room, which is this Zeno dragging. And so this is implemented in a low frequency qubit where you're kind of, instead of looking at the typical energy eigenstates, you're instead looking at the time-dependent kind of Hamiltonian, like Rabi eigenstates. This is my understanding, but I'm sure experts can correct me. And you have a tunable measurement axis that you can adiabatically drag by just changing this angle delta. And so what you can see is that essentially this allows you to drag the state from an initial state to a target. And sometimes you'll get these runaway trajectories where you'll get a jump to the opposite state because it's a finite measurement strength. You can't completely remove the presence of jumps. And so this is a selective realization because you can actually track if trajectories ran away and post-select to remove them if you're trying to prepare this state, for example. And here it's actually the adiabatic change of the measurement axis that kind of provides the competing evolution here, just like our Rabi evolution provided that competition. So you can also do this, use the Zeno effect to do things like entanglement generation. So in this experiment by Blumenthal et al., they started with a Hamiltonian that was independent between two qubits. So just kind of local evolution on each qubit. But then by doing a measurement of that is joint on the two qubits of whether it's in this particular qubit state or not, you can basically project onto a subspace where the evolution is an entangling gate. And what that looks like in this, in the Hamiltonian is you can actually look at the kind of bare Hamiltonian and just apply this as a projector, sandwiching it, and the local Hamiltonian you had becomes an entangling evolution. So you can get non-trivial dynamics in this smaller confined subspace. And so they did actually observe increased concurrence with their Zeno drive amplitude and were able to prepare an entangled state. Another application I mentioned that, well, so this is like a photon blockading experiment. And so the idea is that if you measure, are there less than n photons or there n photons or more, you can actually just confine your state to have less than n photons by making this measurement very strongly. And this kind of measurement, they typically will do in a dissipative way. So they won't even get a measurement record. And what you're looking at here is, let me explain this. So you can see basically that for various photon numbers n, the populations of the various Fox states in their system are confined to whatever Fox states are below that photon number. So they successfully confine their state to have below a certain photon number. And you can see that basically in their Wigner function, this dashed line corresponds to states that are less than that photon number, and all their evolution happens within that space. So it's kind of like, you can think of it as a state preparation kind of experiment. I also mentioned earlier this dynamically protected cat qubits experiment. So in cat qubits, right, your qubit is encoded in your parity state. So these two states, this C alpha plus and C alpha minus, these are even and odd parity states, bosonic states. And the idea here with the Zeno effect is basically that you create a evolution that is has a 2-photon drive and dissipation process. And by making it a 2-photon process, you're going to essentially confine, like your parity states are going to be eigenstates of the 2-photon driven dissipation. And this actually makes these parity states very stable under your evolution. And it's not always practical to actually just be reading out what is, or you don't necessarily have to read out what is the parity of these states, though you probably will want to for error correction. But the point is that by measuring the parity strongly, even just using a dissipative process, they can stabilize their qubit states against bit flip errors. I'll just breeze through this one, but basically this is an example where they actually tracked jumps between these kinds of parity eigenstates. So you can imagine that just by measuring the syndrome of your states, you can actually also eventually do error correction that also suppresses errors. And this is, we're getting close to the end. I know this is like a lot of examples, but so in this experiment, which was a kind of a repeated quantum error correction experiment, they thought to compare like how does the average state fidelity, if they're just trying to preserve a state, how does that evolve over time if they do no error correction, which is kind of this green and blue, if they do error detection, but they don't add the correction, which is no feedback, this gray, or if they do the detection and the correction, which is this purple. And what's really notable here is that the biggest increase in state fidelity actually came from this detection step. The correction step is kind of like a little improvement on top of that. But I think that's very telling in that this is kind of what you expect from the quantum Zeno effect, passively suppressing errors. And the correction is kind of a additional boost on top of that. And this is, again, something really underappreciated because people tend to think of error correction as you're correcting incoherent errors, but a lot of errors actually are coherent or they're non-Markovian in some way, in which case the Zeno effect will suppress them just by the detection step. The anti-Zeno experiments that have been done have basically just been demonstrations that we see this effect. I'm not going to go into much depth other than saying, you know, it's been measured primarily actually with mimicking a bath spectral density and a measurement that also is mimicked via a noisy drive. So they typically haven't been done with actual measurements, you could say. but they were able to observe these effects. And I think that part of why like we see a lot of practical applications now of the Zeno effect, but not of the anti-Zeno effect, is just that it's not that the anti-Zeno effect is like totally useless. It's just that there hasn't been that much appreciation of it or understanding of how it connects to the Zeno effect. But as we saw in those trajectories, it allows you to tune a tunneling rate between states that are otherwise separated by tuning your measurement rate. And this essentially is like a tunable tunneling rate between subsystems, which is part of the result of this paper out of Andrew Jordan's group of capturing an electron in the virtual state. And so, you know, I'm coming from a superconducting qubit background, so thinking about this in a superconducting qubit perspective, you could just think of this as like a measurement induced swap gate where you can tune whether your qubits are swapping or not. And if you measure one of your qubits, you can just stop once your excitation is swapped. So it's has potentially useful applications. I think the other way to kind of think about why understanding the anti-Zeno effect could be really relevant for applications is that it just gives a more nuanced understanding of how error suppression works. So if we have a peaked bath spectral density that is detuned from our system, which in general, I think it's a good assumption to assume that not all interactions are going to be resonant. It kind of points the way that if we want to suppress these kinds of interactions with a Zeno effect, we need to aim to measure faster than whatever that detuning is. Otherwise, we're going to kind of create more problems. And so, yeah, so this is kind of where I see potential applications. And I think that's part of the hope in this paper that we recently put out, is that people will kind of pick it up and be like, oh, like this anti-Zeno effect isn't so weird or different than I thought it was. Maybe I can use it in this way, you know. And so just to summarize, you know, we saw that the understandings of these effects diverged based on the measurement selectivity or whether the bath is or competing evolution is detuned. In other words, is it orthogonal or not to our measurement axis? But our minimal model is a simple demonstration of how these effects arise in all of these scenarios and just manifest differently based on whether our evolution is stabilized or more standard. And so we can see from recent experiments that we can apply all of these effects in a variety of contexts, but stabilized effects have largely been unexplored so far. So that's it. Thanks.
Thank you, Sasha. I think that we have time for plenty of time for questions. So what are your questions? Either here or from the online audience.
Or complaints, and also
Yeah, right.
concerns,
I mean,
Perhaps you can do like a post survey.
a post survey.
Yeah.
Should we go back?
I have a comment on, it's not really directly relevant to what you've done, but in the early parts of the talk where you were talking about all these sort of flurry of papers about the Zeno and anti-Zeno effect and what, you know, what constitutes a measurement of it. I remember when that was happening. That was happening when I was doing my PhD, and I found it incredibly annoying. Every day I'd go into the archive, look at the new papers, and I was like, I have to get wade through 3 or 4 papers arguing about the Zeno effect and anti-Zeno effect, or I got some interesting stuff. And then but I always thought at that time I always thought that this debate could really use somebody with a background in quantum foundations looking at these issues, because part of the question has to do with, well, what constitutes a measurement having been done and what doesn't constitute a measurement having been done. So that was always part of the debate about, whether we could consider this to really be a Zeno effect or not.
That's cool.
Just clarify to you.
I mean, it doesn't, I mean, it sort of, and none of it was like especially surprising. It's how I expected the story to go, although I have never seen the story worked through like this. But if I had to guess that how it worked, I would have said something similar.
Said it was trivial.
It's not trivial, but it makes sense.
I think it's kind of obvious in retrospect.
Yeah.
I think that's like once, because there's a poster thank you. There's a poster I've given a few times, and whenever anyone looks at the anti-Zeno resonant tunneling example, they're like, oh, yeah, well, yeah, of course, and then it's like, but yeah, obvious in retrospect.
Maybe I can make a comment that I think as human beings, often when we have a label or a bucket, we want to, that kind of becomes a touchstone, and everyone wants to throw things that they kind of think are like kind of like that into that bucket. I feel like the Zeno anti-Zeno thing has become that bucket for people to sort of like, if something is kind of like it, they grab it and put it in that bucket, even if the bucket doesn't really fit.
Mm.
So for example, like when I look at this paper by Krzyzewski about his picture of anti-Zeno as bringing some bath degrees of freedom in resonance, and your line width is becoming broadened and blah, 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 blah. That's sort of one story you can tell and kind of way of thinking about this physics. But when I think about, doing a measurement, getting information, looking at quantum back action, that's a very, very different picture from this Krzyzewski approach. And so I think I tend to think of them in very different ways. I think there are ways you can connect them, but many of these effects just seem like new effects to me. Like the fact that you have this delta bigger than omega R effect, just seems like a different effect to me. And so I think there are ways of connecting them, but I think we need to be more open to just saying, hey, I discovered something new, and maybe it has some connection to this other stuff, but maybe not. Maybe it's just something new, it has new features, and just to embrace that. So don't call it the Zeno effect, call it the Sacha effect.
Yeah, I mean, I think I'm curious, so is part of your point here that, is this really the same anti-Zeno as Kaufman and Krzyzewski were?
I would
kind
say
of pointing
no.
out?
I would say
Yeah.
no, not at all.
Because of the selectivity.
Exactly, it's a whole different insight, it's a whole different set of physics, a whole different set of information. It opens up in a way that it's very different than this picture of just spectral broadening.
It's interesting, as this sentiment is very similar to kind of where our discussion started, where the objection you're raising was more or less my objection. It's like, why are we calling this Zeno? This doesn't seem to have anything to do with Zeno. And I got
To me, this seems more appropriate to call this the anti-Zeno effect than the other one. This seems to have a lot more to do with similarities to the quantum Zeno effect than is actually called the anti-Zeno.
That's exactly why we ended up writing this, is to say, okay, this is something we can precisely connect to Zeno. I don't know what the other one was, but this we can defend.
I think it is interesting though, this thing of like, if there's a bucket, everyone wants to throw stuff into it. Like, there are these recent papers that are like, well, like, the Zeno effect isn't limited even to like measurements in a dissipative sense. You can replace it with interrupted unitary evolutions. And it's just like, okay, at some point you just have to be like, okay, obviously if I have one evolution that is orthogonal to another, they're going to interfere with one another because they don't commute. Like at some point you just have to draw the line and be like, am I just saying everything is the Zeno effect because everything non-trivial has to do with things not commuting with one another. So I kind of get where you're coming from of like, okay, why are we throwing all these things into buckets, into these, like these buckets are maybe so large that they aren't buckets anymore. Also, yesterday I was giving my poster talk at USC and someone was like, I want to understand this anti-Zeno effect. And he's like, so a professor of mine was describing the anti-Zeno effect and then he goes on to describe this. And I'm like, that's what I would call Zeno dragging. And he's like, oh, it's like people use the word anti-Zeno sometimes to refer to Zeno drag. Because I guess because it's moving, so the arrow is moving.
So I come from a nuclear community, and people started thinking about on these lines because it turns out that we should expect from the theory the deviation from exponential decay rate in nuclear decay, but as I know, nobody observed it. And one of idea of possible applications of Zeno anti-Zeno effect will be like fuel processing, you know, stop it from decay, or even better, use anti-Zeno effect, decay it even faster, because when you switch off the machine, then it still decays normally. Can you comment on it?
So
Would it be possible to, in principle, it's just
so I think
technical problem?
what you're pointing out here of like the how the initial evolution is like that we like what you said of we haven't actually seen a deviation from exponential decay.
Yeah, in nuclear decay, no, as I know it.
Yeah.
They try it a lot.
And I think that's part of that would be, and maybe this is what you're pointing out, but that's part of the difficulty in applying it in a case like that is that you need some sort of non-exponential process that you're competing with because the measurement otherwise has nothing to kind of grab onto to interfere. Like two Markovian processes can't kind of stop each other. And I think, anyway, so it is interesting historically, you know, a lot of people were interested in inhibiting the decay of particles, but that turns out to be a really bad example for the quantum Zeno effect because, as you say, that's one of the processes where it really seems to be exponential.
They have not been able to find this non-exponential decay part because you know from the theory. Well, when you have only one particle, then you cannot speak about exponential decay. You must have collected. And initially, you can easily show that it cannot decay exponentially when time evolution is very short. But nobody seems to be able to see this in case of radioactive decay experimentally. They tried it a lot to get information about state nucleus interaction inside, etc. So is it possible to think about some kind of Zeno setup when you can basically stop it, reduce it, and to see this initial part?
Yeah.
Or in total practical terms, you know, to have like universal fuel processing plant, you know?
It's a hard question.
Yeah.
It's
Yes,
hard
but
to
this
answer
is
right now.
Institute for Quantum Studies.
I mean,
I don't expect an answer. This is just like discussion.
yeah. I mean, I guess my instinct is like, if there, you know, if someone wants to answer this question of, is there a non-exponential part, you know, measuring it really strongly and seeing if there's a change in the decay rate would be one way to try to probe that. You know.
Yeah, my point.
Yeah, so,
Have you
but I don't
thought
know,
about
like, I
this
don't know
line?
what has been done in
Like
this.
it is not practical, you know, or something like that?
I don't really know much about like nuclear decay implementations. I'm not sure like why or why not it wouldn't be practical, but I'm also not sure if people, yeah, I don't know, like when I did at some point look into the history of kind of more quantum jumps from this nuclear decay perspective where people were reading out to kind of see like the time process of the jump itself. But I didn't see any discussion in that history of like that jump rate being modified by the fact that there was like by the strength of the measurement. So I actually don't know if that's been studied in nuclear systems. I know like some like there's been some I think like ion experiments, but I don't really know.
I'd really like to discuss this a little bit more, especially about ions, but we can do it afterwards. And I have something to show you.
Seminars like he's bringing up like new collaborations and that's good. So more questions either from here or from people on Zoom. I'm reading that as a no. So let's thank our speaker again. I have two reminders. First, next week we will have Ahmed from Berkeley. It's going to be a Zoom. It's going to be a Zoom seminar. And tomorrow, especially, we have another IQS seminar by Fernando Brandão, this chap from Caltech and Amazon. He's going to talk about like error correction. And the title is Scale Efficient Quantum Error Correction Using Concatenated Bosonic Qubits. 2 p.m. tomorrow, conference room B. And then it is the one I also like mix it.
And anecdotally, I did look at the abstract and some of that is kind of using dissipative stabilizing effects. So you can go to the talk and reflect more on, is this the Zeno effect? You can ask the speaker.
Maybe all our correction is the Zeno.
There you go.
And this will be in-person talk?
In person, yeah. Yeah, he will arrive here tomorrow at 11 a.m. We will have lunch together and then at 2 seminar and then we'll stay.
So maybe we should get a schedule together for him to visit people while he's here.
Yeah.
This would be good.
So yeah, that's all. Thank you.
Easy.